Hello everyone, I am Adnan Sadi and today I'm going to talk about a dynamic programming problem known as the Levenshtein distance or the edit distance. Now, Levenshtein distance is the minimum number of edits required to transform one string into another. For example, we want to transform the string kitten to another string sitting. Now in the first step, we can replace k with an s. Now notice the next three characters in the string are same in both cases. So we don't need to perform any operations here. We need to perform operations only when there is a mismatch. Now on the next step we can transform this E with an I. And finally we can insert G at the end of the string to complete our transformation. Now notice we needed three edits to complete this transformation of kitten to sitting. Now this is known as the edit distance, and which in this case is 3. Now there are two situations that can occur while comparing the two strings. One is obviously that two characters can match, and then we don't need to perform any operations. But if the two characters don't match, then we can perform one of these three operations to edit the string, and they are insert, delete, and replace. In the upcoming slides, I'm going to talk more about these three operations. Now, let's say we want to convert the string bird to another string duck. So, firstly, we want to compare the last character of each of these strings. And here we can see that the last character don't match with each other. So what we can do is we can insert this k at the end of the first string. So now the last character of both of these strings match with each other. So on the next step, all we have to figure out is how we can convert this substring BIRD to this substring DUC. Now there is another thing we can do which is delete. We can simply delete the D from the bird when we see that the last characters don't match. So now what we have to do is we have to convert this BIR to this string DUCK. Now also the third operation we can do in this case is we can replace this D with an K. So now these two characters match with each other. So on the next step we simply have to convert this substring BIR to this substring DUC. Now, if we want to solve this problem in a brute force manner, what we can do is follow the greedy approach, and that is we divide this problem into small sub-problems and then find solutions for these sub-problems. And we will finally choose the solution that requires the least number of steps, which is the optimal solution. In this case, which would be the minimum number of steps required to convert this string into these strings. But there is a problem to this approach, and that is here we can see that there can be certain amount of repeating subproblems, and we know when there are repeating subproblems we need to use dynamic programming to find optimal solution. Now let's find out how we can use the dynamic programming table to find the minimum edit distance. For this example, I'm going to transform the word replace to the word delete. So the first thing I have to mention is what each cells of this table represents. So let's say that we are at this cell. What does that mean? It means that we want to convert this string RE to this string DE. So as we can see that each cell of the table represents a subproblem, which is a really important thing to remember. Now let's see how we can fill out this table. So when we are at this cell, it means that we want to convert this empty string to an empty string. And the cost for converting an empty string to an empty string is 0. Similarly, for the cell on the right, we need to convert this R into an empty string. So what we need to do is we need to simply delete this R. So that is one operation. Similarly, on the next step, we need to convert this RE to an empty string. So we need to perform the delete operation twice, and so on along this row. Now if we consider this column, uh, what we need to do is we need to convert this empty string to uh, the string D. So we need to perform an insertion, and on the next column we need to perform two insertions, on the next three, and so on. So this is how you fill out the first row and the first column of the table. So now comes the interesting part. Let's say this is my position on the table. So the cell on the left represents the delete operation. The cell on the top represents the insert operation, and the cell on the corner represents the replace operation. So we need to pick the minimum value of these three cells and then add it with 1. Now we need to do this only when there is a mismatch. So let's come back to this cell. We can see that R and D does not match with each other, so we need to pick the minimum value of these three cells and then add 1 with it, because we are performing operation. So the value of this cell would be 1. Similarly, for the next cell, we need to pick the minimum of these three cells and add 1 to it, because we are performing an operation. So now we see there are two minimum values. We can pick either one of them. In this slide I'm going to pick the one on the corner. Similarly, we can fill out the rest of the cells, because we can see there are no characters that matches with D. So we pick the minimum value and then we add 1 to it. Now on the next row we can see there is a mismatch between R and E. So we need to again take the minimum value and add 1 to it, so we have 2. But in this cell we can see that there is a match. So let's try to understand what is happening here. We can see that we need to convert the string RE to the string DE. But since there is a match on the last character, we don't need to consider this character anymore. So we have to simply convert this R to D. And the cost of converting R to D is 1. So this is the value we need to pass to this cell. Similarly, on the next cell, you can see there is again a mismatch, so we need to pick the minimum value and we need to add 1 to it, which is the case for the next three cells as well. And on the last cell we can see that there is again a match, so we need to take the value on the corner and pass it over here. So similarly we can fill out the rest of the table. I'm just going to quickly fill out the rest of the table here. So this is the final table that we get, and that this value at the last cell is the minimum edit distance value that we required. So this means that to convert the string replace to the string delete requires 4 operations. So how do we know that which operations we performed? To do that, we need to simply backtrack our whole simulation and how we got the values. So let's say the first operations are performed here, and we took the value from the corner. So we can see that the value on the corner represents the replace operation. So what do? We replace R with D. And the next operation was performed over here, and we can see that we got this value by adding 1 to the value on the left. And from the table you can see that the cell on the left represents a delete operation. So what we did here is we actually deleted P from the string. And the next operation was performed in this cell, where we replaced replaced the character A with E. And the last operation was performed in this cell. So as you can see, we performed the replace operation, so we replaced C with D. So if you wanted to see the simulation, this is what happens. First we replace R with D, then we delete P, and next we replace A with E, and finally we replace C with D, and this is the target string that we are looking for, which is delete. So this is how we can use dynamic programming to figure out the minimum number of operations required to convert one string to another, which is also known as the edit distance. Thank you everyone for listening to me.